Hello, this is Mrs. Taylor, and I'm going to introduce you to U substitution or change of variables, depending on which textbook you're looking at. So what we are trying to do is integrate using U substitution. And what we know so far is we have our fundamental theorem of calculus that sets us up to understand that if I integrate on an interval from a to x, we think of this as the accumulation function. So it represents how much area accumulates on that given interval. And the upper limit's represented by x to show that that interval could change, and so your accumulation changes. And then the second part of the fundamental theorem of calculus states that your derivative and your integral are inverses. So if I were to take the derivative of this accumulation function, I would pretty much end up with the integrand of my original accumulation function. And so basically it's taking this upper limit of integration and plugging it in for your variable in your integrand, which you end up with f of x. Now, another thing we discussed in class is what happens when your upper limit of integration is no longer just x, but a composite function. And typically, we represent composite functions with the variable u. It's pretty much a universal indicator of composite function. And so we discussed in class how you still would use this same concept of taking your upper limit of integration and plugging it in for x, but you have to remember it's kind of like the chain rule where you have to compensate for the composite nature of this function. So not only do you take your composite function and plug it in for t in this particular representation of the accumulation function, you also have to include the derivative of your composite function. So taking all that information, we are going to move into U substitution. So, the role of substitution and integration is comparable to the role of chain rule in differentiation. And so in differentiation, our chain rule, if I were to represent it with some notation, is if we are taking the derivative with respect to x of a composite function, so let's say f of g of x, then we would take the derivative of the outer function, leaving the inner function as it is, and then multiply by the derivative of the inner function. So, if I'm working backwards and I'm integrating, the idea is, and we'll write therefore, if I integrate this here, so if I have f prime of g of x times g prime of x dx, this would simply equal your composite function, so f of g of x. And recognize we don't have an upper and lower limit of integration, so we include the plus c to show that this is a general solution. And so the idea is if you were to use U substitution, you could write let me rewrite that. If u equals g of x, then du equals g prime of x dx. Remember, you have to accommodate for whatever the derivative of this inner function could be. And so when we use substitution, we could rewrite our original integral here as the integral of f prime of u, because remember we're letting u equal g of x times du. And so the whole purpose of this is this particular integral can be often more simple to work with than this integral. And so the idea is U substitution makes integrating easier. And some of those rules that you're not able to remember through pattern recognition, you can still get to the right answer using U substitution. So, we have two methods of finding antiderivatives of composite functions. What we've been working with is pattern recognition, which is your simple, straightforward situations. So this is where we have 1 over 1 plus x squared, and we recognize it as inverse tangent. Or 1 over x, and we recognize that as the derivative of natural log of x. Those are the pattern recognition composite functions that we can integrate just based on what we know about derivatives. Change of variables, or U substitution, are for the more complicated ones, the ones that we don't recognize a pattern, and we need to better gauge what exactly the outer function might be. And so let's work through a couple of examples to kind of fully understand how the U substitution process works. So in this problem, we are integrating 2x times x squared plus 1 all raised to the 4th power dx. And so what we want to do is we want to find a way to use U substitution so that we are creating an easier integral to compute. And so a lot of times your U is going to be your inner function. So think about this as 2x times this composite function here, this function raised to the 4th power. So if we let U equal x squared plus 1, then du would be equal to 2x. And so once I've established what u and du equal, I can rewrite this integral with those two variables substituted in. So instead of writing x squared plus 1, I'll just write u. And instead of writing dx, I write du. And actually, instead of writing 2x, I would write du. And I forgot that the derivative would be 2x dx. You have to remember your differentials. So we are not only replacing the 2x, but also the dx. And so my integral would be transformed into just u to the 4th, because x squared plus 1 was replaced with u, and 2x dx, both of these terms, were replaced with du. And because we're multiplying, remember multiplying is commutative, so I can replace terms that are not directly next to each other when they're being multiplied. And so this is an integral that I'm very familiar with. I just add 1 to the exponent and divide by the new exponent. So this would be u to the 5th divided by 5. And remember, there is no upper and lower limit of integration, so include that plus c. My final step would be to substitute what u equals back into my final answer, because we're integrating with respect to x, so our answer needs to be in terms of x. And so my final answer would be x squared plus 1 all raised to the 5th power, all divided by 5 plus c. And so that's how I would use U substitution to integrate a composite function.